This video is what I call advanced pedigree analysis. What this is when we have a pedigree where things aren't really straightforward. So an example is shown here. So here is a family that has some inbreeding. So we have two cousins that have married each other, and albinism, a recessive autosomal disorder, runs in their family. Now, as you look at this pedigree, what you quickly realize is that you can't actually tell for sure whether the parents involved, these two individuals in generation 4, are actually carriers or not. In order to figure that out, you're going to have to go back, look back one or more generations, and see if you can figure out a probability that each of these parents is actually a carrier for this albinism disorder. When we look at these kind of problems, I want to give you a couple of guidelines to start out with, and then I'm going to work through a couple of these problems. So first of all, I usually think it's easiest to actually write on a pedigree. So write down what you know for sure. Figure out what genotypes are known for sure. Then you're going to go back one or more generations, figure out at what point you can assign a probability that you can be confident about. And then you're going to use the multiplication rule to figure out the overall probability of certain events. We'll work through these steps in just a minute, but I want to tell you first of all a couple of things. So when you have a very rare disorder, this is a genetic disorder, we generally assume that an individual who is marrying into the family is not a carrier if they have no family history of the disorder. In contrast, if you're looking at something that is fairly common in the population, such as a polymorphism, you actually cannot assume that an individual is not a carrier who is marrying into this family. So I will generally try to let you know what assumptions you can make regarding these kind of situations. So here's our first example. The very first step is to label the genotypes that we know for sure. And so I usually start with the homozygous individuals right here. And any parents of homozygous recessive individuals have to each be heterozygous. In addition, if you look at this family right here, what you see is that the mother is homozygous, so the only A allele that she has to give is a little a. So all of her children are going to have one little a, and since they are not affected with the disorder, we know that they each got a big A from their dad. So the question is, what is the probability that the child of these two individuals is going to have albinism? And we know that the father is actually definitely a carrier at this point. What about the mother, however? So the mother could be either big A or big A little a. And let's think about what the probability is that she is a carrier. So her parents are heterozygous, and if I write out the Punnett square here, she is not affected with the disorder, so we know that she's not that. So there are three possibilities. Two of those possibilities are that she is a carrier. So the probability that overall that she's a carrier is 2/3. Now there's another important probability to consider here. So if both of them are carriers, what is the probability that their child will be affected with albinism? That probability would be 1/4. So now we have two probabilities to consider, the 2/3 and the 1/4, and we have to multiply them together because both of those things have to occur in order for the child to be affected with albinism. And we get 2/12 or 1/6. Here's another example. This one is somewhat more complicated. We're going to start out by labeling genotypes. I'm just going to label the genotypes that are relevant in figuring out whether these two individuals are carriers. This is, again, an autosomal recessive disorder, and we have the same question. What's the probability that the first child of these two individuals will be affected with the disorder? So, first question, affected, therefore the parents are both carriers. And here, this is a situation just like we had before. We know that this man is not affected with the disorder, so that possibility is removed. And so there's 3 possibilities, and there's a 2/3 chance that he is a carrier. So the dad is 2/3 chance. What about the mom? So the mom is more complicated. So we're going to go back and we're going to look and see at what point can we know a probability for certain. So we don't know whether her mother is a carrier or not. So we'll have to go back yet another generation, and I'm going to first write down the genotypes. So here we have a homozygous recessive individual. Therefore, this man and all his siblings must all be carriers. The little a is the only allele that he could get from his mother, and he's unaffected, so he has to have received a big A from his dad. In this example, this is a very rare disorder, so I'm going to tell you that any individuals who marry into the family, if it's not otherwise indicated, you can assume that they are homozygous wild type. Okay, so this individual, big A, big A. This individual also will be big A, big A. Okay, so now this cross is different than the one we saw before. There's only one kind of allele that can come from the mother here. From the dad, it's either big A or little a. And so all the children here have a 1/2 chance of being a carrier for the disease allele. So this woman is 1/2 chance. In the next generation, what we're going to do is we're going to briefly assume that she is a carrier and think, if she is a carrier, what's the chance that she would have passed on that allele to the next generation? Don't worry, we're going to remember to take into account this probability, the fact that we don't know for sure whether she's a carrier. So if she is a carrier, this is the same cross as the previous generation, big A times big A, little a. And the probability of being a carrier, of her child being a carrier, would be 1/2. Okay, so now the overall probability that this mom is a carrier is going to be 1/2 times 1/2, or 1/4. Last thing we need to take into account is the child. And if these 2 individuals are both carriers, the chance of an affected child would be 1/4. Okay, so now we need to multiply all of these probabilities together because all of these things need to happen in order to have an affected child. The overall result is 2/48 or 1/24.